Dalton's atomic theory stated that an atom was indivisible and indestructible. However, in 1886, Goldstein came upon positively charged radiations in a gas discharge, which he termed as canal rays. These radiations led to the discovery of proton. The mass of a proton was about 2000 times that of an electron, and it carried a positive charge. Around the year 1900, J.J. Thomson did experiments on the beams of particles inside a glass tube called the cathode ray tube. He found that the particles were attracted to the positive terminal of the tube. Thomson concluded that the particles must be negatively charged and called the particles as electrons. An electron has negligible mass and has a charge of -1. These mean that scientists believe that an atom was divisible and made up of electrons and protons. What they didn't know at that time was how these electrons and protons were arranged within an atom. J.J. Thomson was the first to put forward a model to explain the structure of an atom. In his model, Thomson compared an atom to a Christmas pudding. The electrons were like the raisins in the pudding, and the pudding itself was like the positively charged particles. This can also be explained through the example of a watermelon. The positive charge in the atom is spread all over like the red flashy part of the watermelon, while the electrons are embedded into the atoms like the seeds of the watermelon. The oppositely charged particles are held together by electrical forces of attraction. Thomson concluded that an atom consists of a positively charged sphere with electrons set within the sphere. An atom to clean neutral as positive and the negative charge within it are equal. As per Thomson's conclusion, the electrons were embedded in a sphere of positive charge, and this conclusion, however, was incorrect. Thomson asserted that the positively charged spread through the atom held the negatively charged electrons due to the electrical forces. This assertion failed to explain many experimental observations. Thomson's student Ernest Rutherford conducted an experiment using gold foil, which disproved Thomson's model. For his experiment, Rutherford used two gold foil, which was about 1000 atoms thick. He made a narrow beam of alpha particles to fall on the gold foil. Alpha particles are doubly charged helium ions and have a mass of 4 atomic mass units. The result of the experiment was unexpected, as it did not follow the structure of an atom as known to the scientists at that time. Rutherford found that most of the alpha particles passed straight through the gold foil without getting deflected. A small fraction of the alpha particles were deflected through small angles. A few alpha particles bounced back. Based on these observations, Rutherford concluded that the most of the space inside an atom is empty. As most of the alpha particles passed through the foil without getting deflected, very few particles were deflected from their path. This deflection was passed by repulsive force of positive charge in the atom. The positive charge was concentrated in a small area within the atom and was not spread throughout the atom as Thomson had proposed. Based on his observation, Rutherford proposed the nuclear model of an atom. The positive charge is concentrated in the center of the atom, which is called the nucleus. The electrons revolve around the nucleus in circular paths called orbits. The nucleus is much smaller in size than the atom. According to Rutherford's model, the electrons while moving in the orbits would give up energy. This would make them slow down gradually and move towards the nucleus. The electrons will follow a spiral path and then fall into the nucleus. Ultimately, the atom would collapse. In reality, however, an atom is stable. Therefore, this particular assumption made by Rutherford was inaccurate. Keeping the shortcomings of the Rutherford's model in mind, Niels Bohr formed his postulates about the structure of an atom. Electrons revolve in discrete shells called orbit. Electrons revolve in their orbits without radiating energy. Within a particular orbit, the energy of an electron is constant. This is why orbits are called stationary orbits or stationary shells. The orbits or shells are also known as energy levels. In an atom, electrons are not randomly placed around the nucleus, but they are placed in a fixed energy levels called shells as per Bohr's atomic model. These shells are named K, L, M and N. The arrangement of electrons in these shells are known as electronic configuration. For example, carbon has 6 electrons. Its electronic configuration is 2, 4. 2 electrons are placed in K shell and 4 electrons in L shell. In order to down the electronic configuration of an element, one should have the knowledge about the number of electrons in an atom of the element. The maximum number of electrons that can be accommodated in any energy level of an atom is given by a formula 2n power 2, where n is the number of that energy level. For example, the number of electrons present in the first energy level equals to 1. According to the formula, 2 multiplied by 1 to the power of 2 equals to 2. So the maximum number of electrons present in the first energy level is 2. According to Bohr's model of an atom, the first energy level K can have 2 electrons. The maximum number of electrons which can be accommodated in the shell L is multiplied by 2 to the power of 2, therefore equal to 8. Similarly, for M and N shells, the maximum number of electrons that can be accommodated are 2 multiplied by 3 to the power 2 equals 18 and 2 multiplied by 4 to the power of 2 equals to 32 respectively. During the arrangement of electrons in the shells, the outermost shell of an atom cannot accommodate more than 8 electrons, even if it has a capacity to accommodate more electrons. This is due to the fact that having 8 electrons in the outermost shell makes an atom stable. There is an exception if the outermost shell is the first shell or the K shell. This shell can hold only 2 electrons. For example, helium has only one shell in its atom. 2 electrons in an atom do not occupy a new shell unless all the inner shells are completely filled. The filling of electrons in an atom is a stepwise approach. Now let us take an example of sodium. It has total of 11 electrons. K shell can take 2 electrons, so let us fill 2 electrons in it. L shell can take 8 electrons. After filling K and L shells with 2 and 8 electrons respectively, we are left with one more electron which goes to the M shell. So the electronic configuration of sodium is 2, 8, 1. Let us now try writing the electronic configuration of chlorine, which has 17 electrons. We fill 2 and 8 electrons in K and L shell. We are now left with 7 more electrons which we fill into the M shell. Thus the electronic configuration will be 2, 8, 7. Electrons in an atom are arranged in a definite shells. The electrons which are present in the outermost shell of an atom are called valence electrons. From the octet rule, an outermost shell of an atom can accommodate 8 electrons. It was observed and concluded that an atom with completely filled subshells are stable and do not react easily. In other words, it means that combining capacities are 0 or nil. The outermost shell of an inert gas elements whose subshells are completely filled are stable. For example, helium and neon, where helium has 2 electrons in its outermost shell and all other the combining capacity of the atom to form molecules either with the same or different elements is called as valency. For example, elements like hydrogen, lithium and sodium contain 1 electron in the outermost shell. Therefore, they can lose 1 electron, so their valency is 1. If an atom contains less than 4 electrons in its outermost shell, the valency of an atom is equal to the number of electrons present in the valence shell. For example, aluminium has 3 electrons in its outermost shell. So the valency of aluminium is 3. On the other hand, if the outermost shell has more than 4 electrons, the valency is 8 minus the number of electrons in the outermost shell. For example, chlorine atom has 7 electrons in the outermost shell. Here in this case, it is easier for the chlorine to gain 1 electron instead of losing 7 electrons. Hence, its valency is determined by subtracting 7 electrons from the octet, which gives the valency of 1 for chlorine. Based on the study made by different scientists on an atom, it was concluded that any atom is made up of fixed number of charged particles called as protons and electrons. Scientists proposed that an atom is made up of two kinds of particles. Positively charged particles are protons and negatively charged particles are electrons. Every atom of an element has fixed number of protons in its nucleus. This fixed number of proton is referred as an atomic number. This number is constant for an element. It is represented by an alphabet Z. Moreover, the number of electrons in an atom of an element is equal to the atomic number of the element. For example, if the atomic number of an element is 12, then the atom contains 12 protons and 12 electrons. Let us examine the element helium. It was found that helium has 2 protons and 2 electrons. However, its mass was found to be 4 times that of hydrogen. Similarly, the masses of some other elements were also found to be double or more than double the number of protons. This problem was solved when James Chadwick discovered another particle, neutron. Neutron is a neutral particle with a mass equal to that of a proton and is present in the nucleus along. The total mass of protons and neutrons reside inside the nucleus. The protons and neutrons collectively are known as nucleons. One atom of sodium contains 11 protons and 12 neutrons. So the mass of sodium is 11 plus 12, which is equal to 23. The mass number is the total number of protons and neutrons present inside the nucleus and is denoted by the alphabet A. Mass number equals to the number of protons plus the number of neutrons. Since the number of protons in an atom is equal to the atomic number of the element, the above relation can be written as the mass number is equal to atomic number plus the number of neutrons. The atomic number and the mass number can be indicated on the symbol of the element. The atomic number is written as subscript on the lower left side of the symbol, whereas the mass number has a superscript on the upper left side of the symbol. Normally, a carbon atom has 6 protons and 6 neutrons, but some unstable carbon atoms were found. These carbon atoms had 6 electrons, but the nucleus was similar to that of a nitrogen atom and had mass of 14. The elements with same atomic number and different mass number are called as isotopes. Isotopes of the same element differ in their physical properties. For example, C12 and C14 are the isotopes of carbon. 1H1 is protium, 1H2 is deuterium, 1H3 is tritium are the isotopes of hydrogen. Many elements consist of a mixture of isotopes. For example, 17 chlorine 35 and 17 chlorine 37 are isotopes of chlorine. If any element does not have any isotopes, then the mass of an atom is taken as the sum of protons and neutrons present in it. But when an element occurs in an isotopic form, then we have to know the percentage of isotopic forms and calculate the average atomic mass. Chlorine 35 and chlorine 37 occur in the ratio of 3 and is divided by 1. The average atomic mass of chlorine atom will be 35 into 75 divided by 100 plus 37 into 25 divided by 100, which is equal to 35.5. Thus, the average mass of chlorine atom is 35.5. The chemical properties of all the isotopes of an element are same. This is due to the presence of same number of electrons. Some isotopes have special properties which were found to be useful in various fields. For example, an isotope of uranium is used as fuel in a nuclear reactor. An isotope of cobalt is used in the treatment of cancer. An isotope of iodine is used. In some cases, it is also possible that the atoms of different elements having different atomic numbers may have the same mass number. Such atoms are called as isobars. For example, argon with the atomic number 18, calcium with the atomic number 20, etc. The number of electrons in these atoms are different, but the mass number of these elements is 40.